All right, let's talk about Chapter 11 in OpenStax, which is solutions and colloids. In particular, we need to talk about solutions. The topics for this chapter are going to be concentrations of our solutions, electrolytes. Remember electrolytes being ions in water? And then we need to consider colligative properties. Colligative properties are properties of a group of particles in solution. And there's a lot of really cool ones, freezing point depression, boiling point elevation, and osmosis, and we're going to go through all of those. Now, in order to talk about the properties of a solution, we have to remember what a solution is. Please remember that a solution, by definition, is a homogeneous mixture. Homogeneous mixture meaning we cannot see the components in the solution. Now we've got three parts on this. We have a solute, a solvent, and then the total. The solute is what is being dissolved. Frequently that is solid. But if it's two things in the same phase, what is being dissolved in our terms of our solute is going to be the one of the lesser proportion. Our solvent is what the solute dissolves in. In particular, the solvent is what doesn't change phase, which means that pretty much anything we put into water, a gas in water or a solid in water, for example, sugar in water, water is going to be our solvent, it doesn't change phase, and these guys are going to be our solute. The combination of both of these is going to be the solution. Now, what dissolves in what? Remember here that like dissolves like. The more similar the intermolecular forces, the more soluble something is going to be into that solvent. So what is going to drive solubility? First of all, with solubility, we know that one substance, a solute, dissolves in another. That's a solvent. And when they dissolve, we say the solute is soluble. For example, salt, NaCl, is soluble in water. Bromine, Br2, bromine being nice and nonpolar, is not particularly soluble in water, but it dissolves very nicely in methylene chloride, a nice organic solvent. If two things do not dissolve, they are insoluble. If in particular it is a liquid dissolving into a liquid, we frequently use the choice of words miscible. Okay? If two liquids are dissolving in each other, they are said to be miscible. It's going to depend on a couple of factors. One, nature likes mixing. Mixing is a tendency towards disorder, that is entropy, and nature really likes entropy. And the other thing that's important is we've got to have good and similar intermolecular forces. What does a solution look like? Remember here that a solution is a homogeneous mixture. So if we took potassium dichromate, this nice yellow powder, and put it in water, we are going to get a homogeneous, we can't see the components, nice solution. Our solutions don't have to involve water. Solutions can be of gases. For example, if we mix helium with argon, we are going to get a solution. It's a solution because it's a homogeneous mixture. We can't see the components, and it's going to be a nice, even mixture. In order for a solution to occur, we have to consider the energetics, meaning that if we're going to take and make a solution, we have to take our solute and break it apart. That process is going to be endothermic. We're going to have to take the solvent and break it apart as well. That is also going to be endothermic. Pulling things apart is going to require heat going in. And then we're going to make a solution. Our solution process is going to be exothermic. If it is too energetically costly for this to occur, our stuff is not going to dissolve. So, back to like dissolves like. Polar molecules are going to be soluble in polar solvents. For example, ethanol with its nice OH is going to dissolve in water. We're going to get nice hydrogen in between this. Also, ionic compounds with nice charges, the plus and the minus, are going to dissolve in our water because we know our water has a partial negative and a partial positive end. Nonpolar solvents with only their dispersion forces are going to be soluble in each other as well. So, for example, carbon tetrachloride will dissolve nicely in benzene. These are both nonpolar. Some molecules have the best of all possible worlds. Soap has a polar and a nonpolar end, allowing it to dissolve in water as well as oil, for example. Soap. Soap is a long chain of carbons where our carbons are going to have all their associated hydrogens, and this can be upwards of 10 or 11 carbons long. Some of these might have double bonds. And at the end of soap, soap itself, not a detergent, but a soap, we have a carbonate. The carbonate end dissolves with water, and so it's going to sit here and interact with our water. And this lovely nonpolar end with all the carbons is going to surround a molecule or a droplet of oil, and it's going to take the oil and dissolve it in water. This is going to be called micellar action. Makes a sphere around our droplet of oil, but because we have one end that is polar and the other end that is nonpolar, we can take something nonpolar like oil and dissolve it into water. In order for this to work, it's got to have the right end on it in terms of the carbonate, or a sulfate if we had detergent instead, and the other end has to be the right length of carbons so that it can dissolve in the oil and still allow the polar end with the carbonate to work with the water. So let's take a quick look at these and decide which is going to be more soluble in water. We know that our policy is like dissolves like. Well, if like dissolves like, that means the more similar the intermolecular forces are, the more it's going to be soluble in water. Well, we know that water is polar, and we know that water can make hydrogen bonds. So we're going to look for things that are either nice and polar or can have hydrogen bonding. So if we look at sodium chloride and iodine, we know that iodine is nonpolar. This is ionic, so this is going to dissolve in water. If we look at methane, which is nonpolar, and ammonia, which we know is both polar and can have hydrogen bonding, we know that the ammonia is what is going to dissolve in water. Again here, benzene, nonpolar. Methanol with the OH. The OH is going to allow it to hydrogen bond to water, and the methanol will be much more soluble. Now, oxygen versus chlorine. These are both nonpolar. Just because they're both nonpolar doesn't mean that they are equally soluble or insoluble. Chlorine is heavier, and because it's heavier, it's going to have greater dispersion forces. Because it has greater dispersion forces, chlorine is going to dissolve better in water. These might dissolve better in carbon tetrachloride. Well, carbon tetrachloride is nonpolar, so we are going to look for the opposite, things that are mostly nonpolar. Potassium bromide is ionic, therefore it will be nonpolar iodine. Ethanol is polar with hydrogen bonding, therefore it's going to be carbon disulfide. If you need to, draw Lewis structures such that you can see the nonpolar properties of carbon disulfide. What about carbon dioxide or HCl? HCl, we know, is polar, so it's not going to be HCl. It is going to be, in fact, carbon dioxide. All right, let's look at terms of solutions. We have a lot of terms that we can use to describe how much we can put in solution. So, a supersaturated solution of uric acid. Gout. Gout is when uric acid, natural byproduct of our digestion, etc., can coagulate and sit and get into our joints. Now, uric acid can crystallize, and these are some really fine pictures of uric acid crystals. And when it can take and it dissolves more than it should, it can actually collect into joints, and these crystals get dissolved in the joints, giving us gout. It starts out with a supersaturated solution, and then the crystals come out of solution, in particular in the joints.